Hello everyone. Today I'm going to show you how we can quickly simulate a transient simulation for an induction machine. It's been often asked that how we can quickly simulate a transient simulation, because for an induction machine, especially if it is a direct online, so you basically give a voltage source. Then if you do not know what is the initial current, then there will be a huge transient current in the beginning. So for example, if you have giving a voltage, but you do not know what is the initial current, then whenever you simulate, you see a very high initial state of current, which takes a significant amount of time to stabilize. But we can smartly initialize the whole problem in a way that we can avoid that kind of a transient in the beginning of the simulations, and that we'll achieve through a locked rotor conditions, where we'll basically lock the rotor side, and then we will scale the conductivity of the windings and the bar in a way that we can damp the rotor eddy current. So let's see how we do it. So first thing first, we need to understand that what is the sleep of this machine. So if I again go back here, it's a 50 Hertz machine. So a 4-pole machine that basically gives us 1500 RPM. And now if we check here the motion setup, and if you go here, we can see what is the velocity of the rotor. It is 1485 RPM. So a difference of 15 RPM. So first thing is that we go here in the project and we create a project variable, and we add here, let's say, a variable name sleep, and the value is 15 RPM divided by 1500. So it is basically 0.01. OK. And we can just say OK. And now what we need to do is that, as I said, that we need to scale the conductivity of the bar. So to do that, we are not going to disturb the main model, but we are going to take a copy of it. So we take copy and we paste it here like this. And now you can see that the same model has been copied here with named as Maxwell 2D Design 2. And for sake of our own clarity, we can rename this one. Let's say I'm going to rename it to source. So it is much easy in that way. I'm going to minimize this one and let's concentrate for a while on this source. So there are a couple of so the reason that we scale the conductivity is because that we want to increase the resistance. So we want to increase, so by scaling with this one, we are going to increase the resistance of the bar. So what we do is this, that we go here and we see what material it has. So the bar, I think it is made of with aluminum underscore Vic with my name initials. And then what we do is that very simple. We go here to the material properties and we clone this material, whatever bulk conductivity it has, we clone it. And now instead of this, I can rename it, let's say, with a slip material. And then what I do is I go here and here very simply I just multiply with the slip. It gives me already the variable here automatically when I type this $sign. I press enter, I press OK, and now I have another material, this with multiplied by slip. So conductivity is now multiplied by slip. So that basically means the conductivity decreases. So that means the resistance has increased. So then I press it OK. So now we have to make sure that all the bar are of that slip material. So I go here, I select all of them. I go to this material and I assign them this slip one. Just to double check, when I go here, I see all those material for the bar. Okay, nice. Well, now we are good. And now another small thing we need to do is that this end connections. That is the thing. So end connection for the bar. So for that also we need to scale. So in this case, since we will be scaling the resistances, so in this case we have to divide with the slip because we want to increase the resistance. So that means that we have to divide it by the slip. So I go again, same thing, I go here $, and then I press slip. And I press OK. So that's pretty much what you need to scale. And then since I told in the beginning that we are going to make a locked rotor condition, so that means that the speed of your system in this case will be 0 RPM. So I make it 0 and said OK. And now finally we want to set up this problem. So a quick checking of the setup. This is too much. I think that we're going to simulate the 2D design one, the one which I showed you at the beginning, up to 0.08 second. So this source model I'm going to simulate till 0.02 second. That is good enough. So we have to always make sure that whatever we put here, this should be smaller than the main target machine or model in this case. So when we simulate this one should have at least more than 0.02 second because it's going to use the initial conditions of this model. So I have like 0.02 second here, and couple of small things we need to check that. So this no, so it will be like this. So this is like because it's this is the first simulations what we are doing. So there is nothing it used from is any previous step. And now we go here in the solver setting, and then it's a good idea to keep it periodic. It will be even faster, and then everything else looks all right. So now I go here and I press analyze. And it has started simulating. At this point, I will stop this recording and I will come back once this is done. OK, so now the simulation is finished. It takes only a couple of minutes actually. And you can see that now the current is here. OK, it's nicely sinusoidal in nature as expected. And then you can see also the torque. If I go here and I press torque plot. OK, but remember this is with locked rotor conditions where there is the conductivity is scaled. So now you got some initialization so in the system. So in terms of your current. So now your goal is to actually simulate your main model, which you are going to tell that, hey, use this initialized conditions in your simulation. So how we do that? So we do not disturb this model. We basically now go here in the analysis and we check the setup. And here, as I said, that we are going to simulate till 0.08 second because we want to simulate a little longer. And in this case, I can go here in the advanced and now start/continue from a previously solved setup. So I want to start not from the beginning, but from the one which I have already set up. So from the source model. So once you go there, then you have this option and you can say that my source project is basically this project. So the moment you click this one, it automatically understands to use the other project and it automatically gives that the source. So this one which we just simulated. And now we have to click these two options, simulate source design as needed and preserve source design solution. So these two need to be clicked, and let's see what here. OK, nothing. And that's it. And I think that this variable mapping probably it's going to ask about sleep. Let's see if I press OK. OK, it didn't ask. And then you go to the solver. And in this case, since we are using an initialized condition, you do not need to reach steady state like this, but you can use the normal general transient simulation. This looks good. And yes, pretty much that's it. So now you will just go here, right click, and you press analyze. Let's see what happens. So whenever necessary, it will also solve the source model, but it normally use whatever initialized value it has from the source. We can anyhow go here and check what are the current and the torque, even now onward. So I can minimize the source so that we don't get confused and go here result and check the current. And as you can see, now we are having a transient simulations, but now the current has not started from 0, but it has taken some initial value already from the source model. And now there is no more transient, but the whole simulation is starting very close to the steady state. So that is exactly what I wanted to show you, that we can very nicely tweak the machine model with a locked rotor condition to get an appropriate initialized value of the current, which we then subsequently use to simulate our transient model. And this will really save your time. So if you like this video, please like my YouTube channel and please comment in the section if you have any doubt. I will try my best to help you out with this kind of a simulations. And yes, if you have any further suggestions for any videos on Maxwell, please let me know also in the YouTube comment section, and I will try to make videos for this channel. Thank you very much for watching it. Before I go, maybe show the torque. OK, the torque is also quite stable. OK, nice. Now I close this this recording.